So today it's lecture 23rd, and you know that I told you in the beginning that we will have about 28 classroom teaching sessions and about 11 or 12 problem solving sessions. So that means, including today's lecture, so I think 5 more lectures I would require in order to complete the syllabus as far as imparting of the fundamentals in heat and mass transfer is concerned. And of course, parallelly we have been doing this problem solving sessions. So the problem solving sessions 11 or 12 together with 28 lectures will fulfill the mandate of the course of about total of 39 or 40 lectures. So let us continue with our discussion where I left you yesterday, and we were talking about diffusion from a sphere, or diffusion more specifically in spherical coordinate system. And we could imagine this process like diffusion through a spherical shell. So there are 2 spheres, one is the inside sphere, there's an outside sphere, that's also possible. But we have posed the problem, as I have indicated, that one way could be that this is a sphere of substance R, A, and then we have the sphere is losing its vapor, and this is the ambient phase, and we can say that this is B. So basically diffusion of A through B, and as I have indicated that B could be stagnant, then we have one kind of a simplification. Also another simplification which renders the process purely diffusion would be that A is sparingly soluble, and so the rate of mass transfer from the sphere to the ambient is extremely small. So the mass fraction of A in the medium is approximately 0, and that will render the case to be pure diffusion, and this I have indicated yesterday. So case 1, therefore, we have the flux expression Na is equal to minus Cd 1 minus Xa and we are considering, because of theta and phi symmetry, so it's a radial direction. So flux of A in the radial direction, one could write also n of A r, where r represents the direction in which the flux vector is aligned, and this represents the corresponding concentration gradient. And then we have the second case where we say that it's a case of these are the 2 possible cases. C is constant, D is constant, and this I have already discussed yesterday. This is for a stagnant surrounding when B is essentially stagnant, and this is for the scenario when Xa, the mole fraction of A in the bulk, is close to 0, which is akin to the situation that the rate of mass transfer from the sphere to the bulk is so low, or the solubility of A, one can otherwise cast it like this, solubility of A and B is small. And if you compare our discussion with the heat transfer, the corresponding heat transfer equation, the flux Q, we have done this, okay, and that is equal to minus K dt dr. That is the radial direction flux, heat flux. That's what was our notation, okay. And if you could look at this, and there is 1-to-1 similarity. This is a case of pure diffusion, and this is a case of pure diffusion of mass, and this is a case of pure diffusion of heat in the spherical geometry, okay. And there is 1-to-1 correspondence because C and D are constant here, so is K, because we are dealing with purely a steady state, one-dimensional radial diffusion in spherical coordinates with constant thermophysical properties. So, and in this case, if you remember, I have shown that Nusselt's number based on diameter is equal to 2. And I have also made that statement, if you remember, that this is the limiting value of Nusselt's number, okay, which tells us pure diffusive heat transfer. And as I said, and we have seen that in the context of convective mass transfer problem, in the same coordinate system, we have additional components which gets added up. The equation. And this equation, I hope you remember, this is a very important convective, force convective heat transfer correlation in spherical coordinate system, and popularly known as the Range-Marshall correlation. And so this additional component comes when there is a fluid motion in the system. Now, obviously, because there is similarity between this and this equation, so we can expect that if we solve this equation, okay, instead of Nusselt's number is equal to 2, this we call as a Nusselt's number for heat transfer, we can have a Nusselt's number for mass transfer also will be equal to 2, because the equation, governing equation and the boundary conditions were identical. This was applied. I can say that at R is equal to R0, temperature was fixed. At R is equal to infinity, temperature was some T infinity. In this case, if we apply the same kind of a boundary condition, that at R is equal to 0, at the surface of the sphere it is fixed concentration, and at infinity also either it is 0 concentration or any other fixed concentration. So the same equation, same boundary condition, and if you define here a mass transfer coefficient in accordance with that, we'll see the definition of mass transfer coefficient later on. But you remember the mass transfer coefficient the way we have defined, okay? The flux at the surface was defined as a heat transfer coefficient times the temperature gradient. That is the surface heat transfer coefficient. So, if the mass flux is also defined at the surface of the sphere in an analogous fashion, that we got to a value for heat transfer or Nusselt's number, we will get for the mass Nusselt's number also, and the mass Nusselt's number in this case we call it Sherwood's number, which is defined as mass transfer coefficient. What is Nusselt's number? The Nusselt's number is defined as the heat transfer coefficient divided by multiplied by the characteristic length and divided by the thermal conductivity of the fluid phase. That's what's the definition. And in this case, the Sherwood's number is defined mass transfer coefficient multiplied by the characteristic length divided by the diffusion coefficient. And this is, note that this is not diameter, this is the diffusion coefficient. The diameter will be denoted by d sub a or d sub 0. So this is diffusion coefficient, and that is the definition. So some people say this Sherwood's number is, for example, mass Nusselt's number. Okay, but we will use as we will see there. So therefore, this we can say that when the case will be in spherical geometry, a case of pure diffusion, analogous kind of a situation can be formulated and solved, giving us a value of Nusselt's number or mass Nusselt's number is equal to 2. But this is a case which is not a case of pure diffusion. There is a bulk motion term which is involved here, and the appearance of the factor 1 minus xa. Okay? And as I said, the moment you put xa is equal to 0, which means the concentration of xa at any point r is very, very small, then this equation and this equation becomes identical. But so long as we don't make that assumption, this is understood that there is a diffusion component here and there is a bulk velocity component here. So therefore, we will not get a value of 2 here, but we will get 2 amplified by a certain parameter, and that amplification will essentially be due to the presence of the bulk motion, and that I want to show through derivation here. And let us now start. So the pure diffusion case is a very straightforward case, that is, derivation is analogous. So I am not interested to show you that. We have done that exercise already for heat transfer scenario. And in this particular case, if you remember, our governing equation was R square Na. So if you do a shell balance, that's the governing equation, and therefore we can say, and I think till yesterday that's what I wrote, and then we can say minus R square, then C and D, 1 minus XA and which essentially tells us that if we do this, the next step would be this is equal to a constant, and let that constant be equal to beta. Or we can say that from this CD by 1 minus XA is equal to, sorry, say dr is equal to minus beta by r square. So we can understand that, or if you let the minus sign here, we can understand that beta by r square value is actually the value of the flux. So flux divided by the r square value will give us, beta divided by the r square value will give us the flux, because the flux expression is this. Let us say that we apply a boundary condition at r is equal to r sub a. We say that x of a is equal to x of a star at r is equal to some r, okay, which say capital R, is this is x a is equal to x a. And this r essentially represents, say, this may be this r. One could put that as r tends to infinity, x a is equal to 0. That is also a possibility. So this is the capital R here as per this, and at this particular case we have the concentration x bulk. So we can solve this equation now, and if you solve this equation, then what happens is that we have minus CD, and if you write down that equation by 1 minus XA, then we can say that this is, and this is beta by r square. Okay, and then we can integrate this. We can put the limit r is equal to lower limit r a to r value. Let us put it RB, because that will be easier. So this is RB, radius RB, and then this is x. Sorry, this should be in terms of x, so I will write it x a star, and this should be x a bulk, and this should be small capital RB. No, this is RA, and then this is going to be capital R sub B. That's what it is. And if you integrate this, so this negative sign will vanish here. So we have CD ln 1 minus XA, okay, minus x, the differential coefficient is minus, so minus minus plus, and this will say XA bulk by XA star, and then we can say that this is equal to minus beta into 1 by r, and this is equal to RA and RB. That's what it is. So we can say that it is CD ln one minus XA and minus, so we can say that is 1 minus XA B by 1 minus XA star, and this is minus beta into 1 by RA, RB minus 1 by or to give it an elegant look. So, we can say that we take this minus off and we can make it minus this, or we can make this A and this we can make B. So, I got the minus sign inside. And as if you further simplify this, then we get the value of beta. Why we are interested? Because beta by r square will give us the value of the flux. So, therefore, we can say that beta can be written in terms of, so R A R B, so I can say it is C D ln 1 minus x A B by 1 minus x A star, and we will have R A into R B, which is going to be there, and we will have R B minus R A, and here we are going to have R A into R B. That is what is the value of the. So, simplification, straightforward transferring from this parameter to the left hand side, we get the value of beta, and we can say that therefore, the flux is equal to this parameter. So, we will say this is R A, so C D R A by R B, okay, into, these are all constants, mind that. This parameter, these values are not variable values, these are all constant. Everything appearing here is constant. C is constant, D is constant, because beta we have derived it, that r square into Na is equal to constant, and that constant is equal to beta. So, all the parameters appearing here are actually constant. Okay? And then we have this multiplied by C D into ln 1 minus x A wow, minus 1 minus x A star. And if we say that we want to do it like this, then what you are going to do is, this now represents the rate of transfer, because I have put the dot here. Okay? The earlier Na was something like double prime, so that was flux, and this is, so I have to multiply this. So, we will have beta by r square, that is the flux. So, let us do it in one step. So, this is Na, which is going to be equal to, that is the expression of flux 1 by r square. Because the entire thing is beta, I have divided it by r square. So, the flux is actually a function of r square, and that is what it shows, that from this particular equation, that r square Na, r square Na is constant. So, therefore, Na is inversely proportional by 1 by r square. That is what is the implication of this equation, and that is reflected here. And this is flux, and if I say the net rate of transport, if I want to do of A, then I will multiply this by the area, which is 4 pi r square, and that r square and this r square is going to be cancelled. So, I am going to have 4 pi C into D, then a r term, which is R A into R B, and R B minus R A, and this is going to be C D ln 1 minus x A B by 1 minus x A star. So, this is our net rate of transport, either in kg moles per second or in kg per second, depending on in which unit you want to express. And this has no r dependence here, as you can see, that this is a steady state problem. So, all the parameters appearing here are constant, which essentially implies that when the flux is inversely proportional to 1 by r square, but the moment you multiply r square with Na, that r square into Na becomes equal to constant. And this is the value of 4 by r square into Na, and that is why this value has come out to be constant. The flux at every r is different, but the net rate of transport, because it is a steady state problem, has to be identical. Now, if you look at the value, for example, there is one possibility here. we can now simplify. So, for example, as I was talking that if you change the boundary condition, that at x r is equal to infinity, r tends to infinity, we have x a bulk tending to 0. If you want to change this, then how do you do it? It becomes very simple. Then it is equal to Na dot, okay, is going to be 4 pi c d and then what we are going to do, we are going to divide it by Ra. So, this is going to be Ra and this is going to be Rb1 minus Ra by Ra. But this term is going to be equal to 0 because Rb tends to infinity. If Rb tends to infinity, then so this boundary that I was talking about, I draw a line here. If you remember, the sphere was here, then I have drawn a line. So, if this boundary, which is Rb, is extended up to the infinity, and that's what I really mean, that the second boundary, which is away from the surface, as it tends to infinity and the concentration gets to infinity. So, I will substitute. Now, this term is going to be equal to 0. So, this is going to be equal to Ra. So, therefore, I am going to get here on the basis of that equation, where Ra is this sphere and then we have ln 1 minus, that is 0, the concentration, and we have minus x star. So, this parameter has become equal to 0. So, we have, and that is what is the term when. So, a simplification I have written it here. Okay. Now, as I indicated that the flux Na at the surface R is equal to Ra can also be defined just like the way we have defined Nusselt's number Km into delta x. Okay. And we can say that this Km, you write it concentration, so it is Kmc into delta x. Either we will write it as concentration in terms of kg per meter cube, or because this is mole fraction, so therefore I have got the molar density here. So, exactly the same way we have defined where this Km represents the mass transfer coefficient, okay, surface mass transfer coefficient, and the flux, the value of flux at R is equal to Ra is defined in terms of the mass transfer coefficient, just like the way we have in the case of heat transfer. We said that at R is equal to R, this is equal to heat transfer coefficient times delta T. The factor C comes here because of the units that I am using for the concentration. If I had used instead of XA, CA, for example, in kg per meter cube, in that case I would not have used the bulk density. Okay? So, the appearance of the bulk density term, or the molar density in this particular case, molar density is because I am using a mole fraction unit. Now, if so, this is going to be delta XA, and that can be now said that in terms of this equation, it is going to be XA star minus 0, because the bulk concentration is equal to 0. Now, if we equate this term, so let us see. So, that is the flux we have, and this is the expression of the flux that I have derived, and I now need that what is the value of the flux at the surface, because that is what I need. So, the generalized expression for flux I have already given you, and that expression is there already on the board. Okay. So, this is the general expression, and this is the flux at any radial distance. So, therefore, I can say that the flux at R is equal to Ra is actually going to be this Ra square. That is what is going to be my flux expression. So, now I can equate this parameter. If I do this, okay, then we have K mass transfer coefficient into C, and then we have x star, and then if we consider this, okay, because I have put this to be is equal to 0. So, therefore, the flux I am going to write, as I have indicated, is in terms of only this term will vanish, because I have already shown that, and this is going to be is equal to R sub A. Because of the simple fact, if you remember that we had R A into R B divided by R A R B minus R A. So, the moment I operated this, divided it by R B, this is R A, and this becomes 1, and this becomes R A by R B, and this term becomes equal to 0, because R B is given a value of infinity. So, therefore, instead of the whole term is now going to collapse into whatever is written here. So, 1 by R square, that gives us that we are going to have this particular parameter. So, the C cancels out, and now we can see that if we do this Km multiplied by Ra, the radius of the sphere, Km multiplied by radius of the sphere Ra, divided by the diffusion coefficient, and that becomes equal to, this value is now 0. So, this is shown to be ln of 1 minus 1 divided by 1 minus x star divided by this x star. That is what comes out. Okay. So, we are doing it Km, we have got it this side. So, the x is on the downstairs, that is fine. Now, Km into Ra, or I can say that if I do it Km into d of A by multiplying this. So, I am going to say that this term is going to come out like this. And what is this? As per my definition, this is equal to the Nusselt's number mass, or which I said I would like to denote, give it a different name, which is in metallurgical literature, it's called Sherwood's number based on diameter. And then you can see that the Sherwood's number diameter comes out to be a fact, 2 multiplied by a factor. And this is the factor that I was talking about. This factor will not come once we deal a pure diffusion situation. That means the pure diffusion in this case will be a situation in which I would have said that, look, the medium is stagnant, and also XA value in the domain of interest is extremely small, so XA can be ignored. So, the bulk convection term can be thrown away, and if that is thrown away, in that case this term will vanish from the derivation, and K, the Sherwood's number will come out to be exactly equal to 2. If you calculate the value, because this XA values is always smaller than 1 could be the maximum value, okay? And this is surface concentration is going to be not 1, less than 1, and therefore you will find that this value will come out to be more than 1. So, it is 2 multiplied by maybe 1.1, 1.2, 1.3 or 2, depending on the intensity of the bulk motion of the gas through the medium. So, this shows us the characteristic feature of 2 that has come here for the spherical geometry again is obvious, and it says that the limiting value will be 2, but in this case also we are not dealing with a direct forced convection scenario, but we see that there is an amplification factor, and this in the context of heat transfer I have explained, by adding up that Reynolds number component as well as Reynolds number and Prandtl number component to the nominal or the minimal value of 2. So, we now know how to deal with pure diffusion situation is exactly analogous to the heat transfer situation. Whatever we have studied in heat transfer can be straightforwardly applied to the mass transfer. The moment you look at that my governing equation is exactly identical to the heat transfer governing equations, there is one-to-one correlation between heat and mass transfer phenomena. Only by manipulating the different time, different property values, you should be able to extract the solution. But if this equation does not match, for example, in this particular case, when we consider that there is a bulk motion of the gas, then there are certain factors which appear additionally into the equation. Then, although same steps could be carried out, but the final solution may be a little bit different because of the additional parameters which arise from the complexity of drift velocity in the case of a solid or bulk motion in the case of a gaseous medium. We can also do a similar exercise in cylindrical polar coordinate system, for example. And we can illustrate it with a diffusion through a spherical shell. Radial diffusion through a spherical shell. The cylinder is treated to be an infinitely long cylinder, so the axial direction mass transfer does not come. So it is the situation that you want to analyze is steady state 1D radial symmetrical and infinitely long cylinder. If you say spherical shell, then this could be, that is the shell. So we have if there is no material medium, we call it as a hollow spherical shell. So in that case, there could be something diffusing here through the medium, which may be a gaseous medium, for example, there is nothing. But in this case, if you want to deal, the moment you consider that this is a solid spherical shell, the diffusion through this we want to consider, it obviously becomes a pure diffusion problem. There is no bulk motion. But if you say that it's a hollow spherical shell, then again the 1 minus xa factor may come here, okay? And in this case, hollow spherical shell will again show us the same characteristic diffusion equation, provided we say that the diffusing species concentration here is extremely small, than the xa terms or the mass fraction or mole fraction terms of the solute within this shell is going to be 0, sparingly soluble material in the ambient. Okay? So because I have illustrated, you know that whatever we consider, whether it is a sparingly soluble or there is a bulk motion, we know how the derivation has to go. To speed up the discussion today, okay, I want to do that this is a dense material, so it's the same material through which diffusion is taking place. So essentially we are talking about diffusion through a solid spherical shell. Okay? So let us now look at that, what is the governing equation. So if you take a small little shell and do the balance here, we will find that the surface area is, and because we are dealing with infinitely long cylinder, so we would like to say that L is not of length of the cylinder is not of our concern. Let us take it that it is L is equal to unity. So everything can be interpreted in terms of per unit length. So L will not be considered in this particular case itself. So you can say that if you look at the surface area, then Na represents the radial. So if this is the, and then we have Na, and this is a spherical shell, exaggerated spherical shell drawn here. So we can do the same kind of a mass balance I have illustrated in the context of a spherical geometry, and then we can write that R, the surface area here is 2 pi R multiplied by L. So 2 pi RL, and we will say that it is at a distance of R, and it is the distance of R plus delta R, and the thickness here we are talking about is delta R. 2 pi RL into Na, and if you do the standard exercise, input minus output steady state problem, so input is equal to output, do linearization, then we will see that this is equal to or this gives us RNA. So you remember now. So if you have a Cartesian coordinate, R does not appear. If you have a cylindrical coordinate, R appears as r to the power 1. If you have a spherical coordinate, the conservation applies as r square Na is equal to constant, as we have seen in the context of the previous problem. So we can now apply a boundary condition, and that so it may be the same problem as you have considered. For example, a gas is diffusing through the solid spherical shell. So the concentration of gas will be known here, the concentration of gas will be known here. So if you want to do it with mole fraction or concentration, that's fine. So let us say that we will write Na is equal to, in this particular case, R. This is our governing equation, or Rna is constant. And from the generalized diffusion equation, you know that Na is equal to minus d. And if you are saying that it is the species which is diffusing is A, and this is. Earlier problem I did it in terms of mole fractions, now I am doing it in terms of the concentration, hence I am not writing the molar density. And if you look at this particular equation, therefore, we can say that and once you have written this equation, so it is as we can say that there is R is equal to Ri, the inside boundary, the concentration of A is equal to CAI. At R is equal to Ro, the outer radius, we can say Ca is equal to Ca outer. These are our boundary conditions which you want to solve. Okay? So therefore, we can look at this and we can say that dCA is equal to and also you note that beta by R is going to be equal to minus Na, the flux, okay, because this term is the negative of the flux. So therefore we can say that we can also write that if you put the negative sign also, it doesn't make any difference because beta is a constant. So we can say that beta by R represents the flux if you take the R here. So now we can say that's what it is. And we can integrate this. Same approach, and that integration limit will be for Ca, we have Ca lower limit and Ca outer limit, and we have R lower limit of R and upper limit of R. And this gives us now, since the flux expression, this derivation I have not shown in the case of heat transfer problem, but that the flux expression is the case we are considering is the pure diffusion, through a solid medium. So the governing equations, diffusive mass transfer equation and heat conduction equations are going to be absolutely identical. So therefore, whatever I am doing here and the results that I am going to show, that will be applicable to a corresponding heat transfer scenario on a one-to-one basis, with diffusion coefficient being, diffusivity is to be interpreted in terms of, for example, thermal conductivity, because we do not have, it's a steady state problem, there is no rho, no Cp, which is associated with the unsteady state heat transfer. So we have, so if you integrate that, then we have Ca 0 minus CAI, that's what it is, and this is going to be beta into ln. We will going to have R0 outer by Ri. Or we can say that d times inside concentration is none, so we can write it like this. And what we have seen here, that beta by R is going to be the flux. So if you do it like this, and you do it like this, so beta by R, as far as this equation here, is flux. So this is equal to the flux, and which is inversely proportional to R. In the previous case, if you remember, I said the flux is going to be inversely proportional for spherical geometry to R square, and for cylindrical geometry it comes out to be, because this is related with the area feature. In one case the area is 4 pi R square, in this case the area is 2 pi RL, and that R and R square dependence comes from basically the characteristic surface features. It is by taking these, actually, the one set of equations can be very easily transferred into other set of equations through coordinate transformations that you must have learnt in some other courses. So therefore we can say that the flux, and so you have written this, the flux is therefore, this is equal to, we have CAI minus CA0. This concentration, if you are talking of gas concentrations, then these C concentrations, okay, can be, so if it's kg moles per meter cube, then this could be, from, if you assume ideal gas law, then these C's can be converted into partial pressures that I have already discussed, that needs to be, need not be repeated in this particular case. And therefore we have this is equal to Na into 2 pi RL and therefore we have this R and this R will cancel out, so we are going to have 2 pi d L. If you want to put, otherwise if you do not put L here, you will interpret this as per unit length. So net rate of transport kg per second or kg moles per second per unit length of the cylinder, but that I have introduced L. So therefore it is understood that this dimension is equal to kg moles per second. And if you look at this expression, everything here is constant, okay. So the rate of first problem that I have discussed, rate of permeation of nitrogen through a platinum foil, that problem in cylindrical coordinate also can be addressed, okay. And in this case you can find out that if the gas is permeating through this, in that case of course this is going to be much more, and this total transport, as you can see, has no R dependence, no radial dependence here, okay. These R's are all constants, inside radius and outside radius, and outside radius minus the inside radius represents the thickness or the path through which the diffusion is actually taking place. Now, so the same, if you can substitute this, convert these concentrations into the partial pressure, then the rate of permeation of a gas through a spherical shell can also be calculated, okay, using exactly the same problem. And the problem related to the permeation of nitrogen through a tungsten filament, which I have discussed, that was with respect to a Cartesian coordinate system, and if the same problem is posed to you in cylindrical coordinate system, and then this is the formulation that can be applied, and where when you convert this to partial pressure, we will have the Sievert's law constants coming in, and that Sievert's law constant multiplied with the diffusion coefficient will give us, as you know, the factor permeability. So I think we will not like to discuss anything beyond this. I am actually I think one and a half lecture behind the way I have taught this course. So I think it is enough for us to know steady state mass transfer up to this level what I have taught. I think that gives us enough background, and it is, I think, we can of course talk about steady state diffusion in 2 dimension and 3 dimension, and as I have indicated, the same philosophy is applied. Okay, every problem we will have the boundary conditions which will be given to us. Okay, so the boundary conditions will be known to us by considering the chemical reactions. This I have told you repeatedly. From the kinetic considerations, the boundary concentrations are going to be specified, and then whether it is a 1-dimensional problem or a 2-dimensional problem. If it is a 1-dimensional problem, you can have an analytical solution. If you have 2-dimensional problem, then of course you will have, as I have indicated in the context of my heat transfer discussion, that you will have some infinite summation series coming up. If you have 3-dimensional, steady state 3-dimensional, you will have a triple sum of cosine functions which will come as a solution for dimensionless temperature field. For a 2-dimensional problem, it is 2 summations. Similarly, for unsteady state heat transfer also, we have seen in certain cases we have a summation series, but the computation of the summation series will require that you take advantage of computer programs or numerical calculation schemes which are available. Alternatively, one can solve the 2D and 3D problems through numerical methods itself, but that is not within the purview of the course. So I think I will not discuss 2D and 3D heat transfer cases, which are not so important for us, because I cannot derive the analytical solutions here, and that will not give us. And steady state solution, we know that steady state 2-dimensional problem, as I have indicated also, if you remember, has no meaning for us, because if you keep the boundary concentration fixed, I mean, you can imagine that's the same problem for heat transfer. If you keep all the boundaries at the same temperature, okay, and then start to solve a 2-dimensional steady state solution, what is the steady state solution? Steady state solution is everywhere within the domain, the solution is going to be equal to the boundary temperature, because it is high temperature, heat will keep on diffusing and diffusing inside the solid till the temperature gradient vanishes. So that problem is of not interest. It is the 1-dimensional unsteady state, 2-dimensional unsteady state, or 3-dimensional unsteady state that are of importance to us, and that is the topic, 1-dimensional unsteady mass transfer problems that we are going to discuss. And in those cases, which we will consider pure diffusion cases, forgetting about the drift velocity and the bulk velocity, and we will see whatever we have discussed in the context of heat transfer will be exactly applicable, because I will be dealing with pure diffusion mass or diffusive mass transfer, and in the context of 1-dimensional unsteady state pure diffusive mass transfer, semi-infinite geometry as well as an infinite slab, and these solutions are going to match exactly with the error function solutions and the infinite series solutions that I have given to you during my discussion of heat transfer. So we will continue with that 1-dimensional unsteady state heat conduction in slab geometry. That is going to be the next topic. The slab will be 2b thickness, and we will pose the problem exactly the same way. Fixed temperature we have done, we will do with fixed concentration. We will henceforth not ask the question that how the surface concentrations are being known. We know that the surface concentrations in the context of our kind of a problem will have to be determined by considering the kinetics only. Okay.